I'm going to talk to you about some of my dissertation work and how we use experimental behavioral neuroscience methods in the lab to help us understand some of the real-world challenges that children with 22q are facing. So today we're going to talk about cognitive control. So what is cognitive control? This is a term coined by cognitive neuroscientists that describes the many tasks that our brains perform in order to help us think, act, and solve problems. This is a system of mental processes that helps one to regulate his or her behaviors in order to achieve certain goals. And so this system is associated with school readiness. Cognitive control has been shown to correlate with success, both academically and otherwise. Obviously, it's important to be able to regulate one's behavior in order to live independently. So this system is comprised of a set of core skills. These core skills being response inhibition, cognitive flexibility, and working memory. So response inhibition includes the ability to resist habits, temptations, and distractions. It's the ability to stop a behavior when wants to inhibit a prepotent response. So for example, if you were here last year, I showed you the video of the kid resisting the temptation to eat a marshmallow because he was right. He was told if he could not eat that marshmallow for 2 minutes, he would get a second marshmallow. But that 2-minute period actually proved to be quite challenging for many of the kids. So that's response inhibition. Then we have cognitive flexibility, which describes how one adjusts to change. So this is the ability to switch between tasks and directions depending on the situation. So for example, here I'm showing you a clip from kids playing freeze dance in a music class where depending on the situation, whether or not music is playing, the kids have to modify their behavior to either dance while music is playing or not dance when the music stops. And then finally we have working memory, which describes the ability to hold information in mind and manipulate that information. And so an example of needing working memory would be to remember the many steps of a multiple part math problem, for example. So cognitive control emerges early in life, but then it continues to mature throughout child development and into adolescence. These changes are concurrent with brain development, importantly the development of the prefrontal cortex, which is the front part of the brain up here, which matures not only through child development and into adolescence, but continues to mature even into the early 20s. And so this brain development is happening at approximately the same time that cognitive control is continuing to develop and become more efficient as children get older and get into their teens. So cognitive control impairments are common in developmental and psychiatric disorders. Impairments in cognitive control have been described in 22q, but the specific nature and extent of these impairments, the degree to which one might have more difficulty in different component processes of cognitive control, those 3 core skills, response inhibition, cognitive flexibility, and working memory. So the degree that these are more or less impaired in this population is less clear. Also, the developmental trajectory of cognitive control in 22q is not clear. Is development in these processes similar to that in other typically developing kids? Are there different rates of development for the different component processes? That we don't know. So one question we would be very interested in is how might cognitive control impairments and their development in 22q relate to challenges that these children face and also potentially to risk for schizophrenia, given that we know that cognitive control impairments are common in individuals with psychopathology. So the way we set out to understand the development of cognitive control in 22q was to test an age range of these children 7 to 14 years old, here at the Mind on a battery of computerized behavioral tasks aimed at measuring each of these component processes in these children. And the way we looked at each one was through a different computer game that was designed specifically to target that component process. So to look at response inhibition, the ability to withhold a response, we had them perform this whack-a-mole game, which I'll tell you more about. to look at cognitive flexibility, or the ability to switch behaviors depending on situations. We had them perform a card sorting task. And then in order to look at working memory, we had another working memory task. So each of these are designed in the form of a computer game that is aimed at being fun for the kids and hopefully will help us give a measure of how efficient these processes are working. So we had approximately 40 children with 22Q and 37 typically developing comparison controls, all in the 7 to 14 age range, on average around 11 to 12 years old, come in and perform each of these 3 computer games. So first, the go, no-go task, to look at response inhibition. So in this task, like I mentioned to you, it's a whack-a-mole game. And so this is the screen on the computer that the children are presented with. And I'll say to them that a mole is going to appear. And as soon as they see the mole, they need to press a button as quickly as possible to make him go away, because he's trying to dig up the vegetable garden, and the children's goal is to try to build their vegetable garden. So I say the mole tries to be tricky, and he wears lots of disguises, but no matter what he's wearing, as soon as they see him, they need to press the button as quickly as they can to make him go away so that he doesn't dig up the garden. So they have one button, they press it as soon as possible when they see him, and but sometimes a vegetable pops up, and as soon as they see the vegetable, they need to not press anything because they're trying to build their garden. So here, we're developing the prepotent response to hit the button because the mole appears more often than not, but sometimes a vegetable appears and they need to not press anything. So 75% of the time, moles appear. 25% of the time, vegetables appear. They need to not squash the vegetable. We manipulate it so that the vegetables appear after either 1 mole, 3 moles, or 5 moles. And so obviously here, the propensity would be to continue to press the button since more moles have appeared prior to the vegetable. All right, so let's see how they did. So first, looking at correct hits. This is how successfully the children pressed the button when they saw a mole. Obviously, accuracy is very high, nearly 100% for both groups. So in blue, we have the typically developing comparison children. Children with 22Q are shown in pink. There is no difference between the 2 groups. So they're both performing the task very well. They're both pressing the button when they see the mole. Down here, this is correct withholding. So this is their accuracy when there's a vegetable. Did they effectively not press the button when they were not supposed to? And for the most part, children with 22Q did very well. This is just overall. Now let's look at by individual trials. So percent accuracy on Go trial number 1, 2, 3, 4, 5 is very high for both groups, and statistically there was no difference. So again, both groups are performing the task very well. Now if we look at percent accuracy on the no-go trials, on the vegetable trials, on vegetables that were either preceded by 1 here, by 3 here, or by 5 moles, we see, if we look at the children in blue, the typically developing comparison children, here percent accuracy is improving when there were more moles preceding the vegetable. And so they did better with more and more moles, 1, 3, or 5. We hypothesize this is because there are only ever 5 moles at most here. So at that point, typically developing children are expecting that a mole might be, or a vegetable might be about to appear, and they're modifying their behavior as such. In the children of 22Q, we did not see that. They had the same accuracy, 70% accuracy across all 3 trial types. So here this is suggesting that potentially when more moles are leading up to a vegetable, the children with 22Q are having difficulty withholding the prepotent response to press a button on a vegetable at that time. So here we're looking at, this is the same graph that we were just looking at, which is accuracy on withholding a response on the vegetable trials. If we look at the response time on the moles leading up to the vegetable, we see that in both groups, response time is slowing with each mole leading up to the vegetable. And I think I could even hear that in this group too, because the more moles that you saw, you're probably expecting a vegetable might be coming up soon, so your response time each time might have been a little slower in anticipation of that upcoming vegetable. So here you're effectively monitoring the context of the situation. And so we see slowing And then this correlates with better performance in the typical individuals here. Interestingly, the children with 22Q are effectively monitoring this context as a group. So they are slowing, similar to the other comparison group. However, for some reason, they are still just not able to withhold that response to press the button to the vegetable following 5 moles. Or overall performance is a little more impaired. So this suggests that this response time slowing suggests typical monitoring of context, but some individuals with 22Q still have difficulty with holding their response. So now let's look at each individual. So this is each individual participant, a scatter plot, showing accuracy to withholding a response on the vegetable trials as a function of age. So now we're looking, doing a cross-sectional analysis to look at development in this age range. We see in blue that the typically developing children are, the older children have better performance than the younger children. So this is what you would expect given evidence that cognitive control becomes more efficient across development. In comparison, the children with 22Q, we do not see this typical age-related improvement. However, it's not in all children with 22Q that the older ones are performing more poorly. Rather, it seems that there's a large spread here. So we call this variance. The difference between the data points is much wider for older individuals with 22Q, suggesting that some of these older individuals are performing very well, very typically up here, and some, potentially a subgroup of the older individuals with 22Q are having trouble with response inhibition. This is just showing that, again, splitting 2 groups into older and younger, showing improvement in blue in the typical individuals, and not an improvement in all older individuals with 22Q. So just to summarize this task, what we see is that response inhibition is impaired in some children with 22Q, and that we did not see that typical age-related association with performance in the children with 22Q, but potentially this is due to a subgroup of older individuals that might have atypical development of the response inhibition. All right, moving on to the visually cued card sort task, which we used to measure cognitive flexibility, or as I described before, the ability to adjust to change or to switch rules or directions based on the circumstance. So for this task, we presented children with this computer screen. It's a screen that they can touch with their finger, and I tell them that the goal here is to sort their deck of cards. Their deck is right here, and they are going to sort their card onto one of these 4 target cards. And they're either going to sort by color or by shape. And they're going to get a clue, that's why it's called visually cued. They get a clue that tells them how they're going to sort, if it's by color or by shape. So the rainbow tells them to sort by color. So here their card is black, that means they're going to sort it onto the black card up here. In the other cases where the clue is a star, they sort by shapes, in which case they would put the triangle on the triangle. So to play this game, they select their card by touching their finger to that triangle. It then becomes selected, and then I ask them to touch the appropriate pile that it should go onto based on the clue. So here with the rainbow, they should hopefully touch this card with their finger, and then they get a great job. This is the other dimension, the other sorting dimension, where they see a star, and here they have to sort by shape, in which case they would put this triangle onto this triangle. So of the 2 different dimensions, the color or the shape dimensions, D1 or D2, one dimension occurs much more than the other one. So this D1 would be the predominant dimension. They're sorting here by color 80% of the time. For the less dominant dimension, they're sorting by shape only 20% of the time. So here again, we're establishing a prepotency, and then when they have to switch rule sets, that requires cognitive flexibility when they go from sorting by color to the next time sorting by shape, for example. And so they sort 50 of these cards, and we looked at accuracy on sorting these two different dimensions. So here on the y-axis, we see percent accuracy. This is just for the card sorting game overall. What we saw is that children with 22q were impaired on this task relative to the comparison children. However, when we split up accuracy into the two different dimensions, the predominant dimension sorting by the main rule set relative to the less dominant rule set where they have to switch the rule on which they're operating, there was a bigger difference between groups. And this difference, the worst performance when switch was required relative to just general sorting on the task, this was a significant difference, and we measured that here by looking at the ratio of accuracy on dimension 2 divided by dimension 1. So here we were hoping to normalize out just general sorting ability and really just focus on switching performance. And what we see is that children with 22q were impaired when a switch was required. All right, so those are the group averages. Now let's again look at the individuals. So here we're looking at percent accuracy as a function of the age range. Let's look first at the comparison controls in blue. The dotted line is the primary dimension. The solid line is the switching dimension. And as expected, the comparison controls show significant improvements as a function of age. Children with 22q, on the primary dimension, so just general card sorting ability, we saw also an improvement with age. Where we did not see the improvement was on the dimension where they had to switch. And again, here's looking at this ratio measure where we normalize the general card sorting ability on the task and are just focusing on the switch. And what we see, again, is that the comparison controls are showing the improvement with age, which is what you would expect to see, but we're not seeing that same trend in the children of 22q. And again, this is potentially due to a subset of the older individuals that seem to have much more difficulty with switching on this task. So this is just to summarize what I just said. While rule switching was impaired, the important thing to note here is that it seems that there are some older children who are having specific issues with cognitive switching. All right, now to get to the working memory task. So here, as I mentioned, working memory, ability to store in mind information. This time, this is what the computer screen looks like, and I ask the children to try to remember each of these objects, and they are going to point out to me a different object each time. So they're going to press their finger to one of these. So say they press their finger onto the bird. The screen then refreshes, and they change location and space. So we don't want them to use spatial information to try to remember the different objects. So the last time they pressed bird, this time I ask them to press a different one. So they might press house. Next time, different one, drum, kite, chair. Now there's one more. I don't think we've pressed car yet. Good. So that's how that would work. You can see it can be hard. So that condition with 6 items to remember is the hardest condition. We had 3 different trial types where they had to remember 3, 4, or 6 objects. So in the verbal version of the task, the objects are items that are easy to name. Then we also had a nonverbal version where the items were more abstract. And then we had 3 different trial types, as I mentioned, where they had to remember either 3, 4, or 6 objects. We saw the most difficult 6th condition. And then the measure that I looked at to examine working memory performance was called SPAN. SPAN was the correct number of responses prior to the first error. So say they pressed bird, chair, car, bird. They would have pressed 3 before doing a repeat, so SPAN there would be 3. So that's the measure that we looked at. So first, looking at performance on the verbal version of the task, if we're looking at the 3 trial types where you have to remember 3, 4, or 6 items, obviously here, best possible span with 3 items would be 3, 4, or 6. So you can see it gets more difficult. Children with 22q had difficulty on this task across all 3 trial types. There's a significant difference between them and the comparison controls. across the board. However, if we look at performance as a function of age, again, looking at the individuals and these scatter plots span on 3, 4, or 6 items, what we see is that children with 22q here are demonstrating improved accuracy as a function of age, similarly to the children with, to the comparison control. So even though there is a bit of an impairment relative to the comparison children, what we see is that this ability to perform on this working memory task is showing improvement as a function of age. So this is suggesting that while performance on the other 2 component processes, response inhibition, cognitive flexibility, might be demonstrating atypical development in some of the children, working memory seems to be showing a more typical improvement as a function of age. This is the nonverbal version of the task, and the results are the same as the verbal version, such that children with 22q have impaired performance on the task. However, we see age-related improvements. So to summarize, performance on the 3 component processes that we're looking at, these 3 core skills that comprise cognitive control. For response inhibition, we see that response inhibition was impaired in a subpopulation of some of the older children in the 7 to 14 age range. Similarly, with cognitive flexibility, rule switching was impaired in a subpopulation of those older individuals. However, age-related working memory improvements were typical in the children with 22q. So this suggests that potentially the impaired performance in a subsample of some of the older individuals on specific cognitive control processes, so not all, it might be certain component processes that might be more relevant targets for us to examine in this, in some of these individuals. It suggests an interesting group to follow with respect to performance on these specific components. So what we can take away from this is that neurocognitive experiments, such as these behavioral neuroscience methods that we have, might help us to better understand the specific nature of cognitive control challenges in children with 22q, and that looking at individual performance patterns might identify those individuals with more and less typical cognitive control abilities. So there might be great information in the variability of performance in the individuals, and that is might provide the most power. And as part of a larger study, this might help us to identify risk factors leading to early diagnosis and targeted therapeutic intervention with respect to some of these specific cognitive control processes. And so the next thing to do is to test a much larger sample of children to try to identify, characterize those subgroups. What might account for this variability in performance in some of the older individuals with this disorder? What intervening variables might account for these differences? And then, as Dr. Simon had mentioned, to conduct longitudinal studies to directly measure developmental trajectory. So this cross-sectional analysis, looking at different individuals as a function of this age range, is an important first step to try to characterize development, but obviously we need to follow individuals longitudinally to see if this holds true in that sense. And then, importantly, to examine the relationship of these cognitive control measures to clinical measures to understand their clinical relevance. And ultimately, if we can understand, this might yield important information to help us with early intervention, which is key because cognitive control processes can be targeted for improvement, which has been shown in a number of studies. So that's where we would like to go in the long run. Thank you very much to my advisor, Dr. Simon, and the rest of the lab, and most importantly to all the families and children who participated in these studies.